because I had no talks. But anyway, it was okay.
The students were fine.
Oh, we have 80 people there. It's not only students, faculties, PhD students.
They listened to him.
What?
Yeah, they listened to him, I said.
Yeah, it was 80 or actually more. The place was 75 places and some 10 people were standing.
Well, that's nice because, like I have checked that on his website, they have what do you call it, advertised the GIAN program thing. So I think he appreciates this activity. So
It was nice, very nice guy. Actually, we had a very nice lunch in his residence also with his wife. It was a nice place. Let me see what I'm going to do. I just have to wake up from the lunch. Okay. Anybody who can see anything here? View. Say stop.
Stop.
Okay, now I cannot mumble jumble, so let me go directly to Hausdorff. So we did all these things. And we ended up with two important things. C11. Okay, so we ended up with C11 and this one. After this is what? So we finish at 3 and then there's a break and then we finish at 4:30?
Yes.
Okay. As soon as I get started, I will wake up. If I get some.
You want coffee?
Yeah, do you think we can make some coffee? It wakes me up at least. So non-degeneracy is also something we did, and we will need this. And we saw that these two together give us that the free boundary has measure 0. Are we familiar with the whole picture? So we had C11, and we had non-degeneracy, and this together gives us that the free boundary has Lebesgue measure 0 through this Lebesgue point theory, which you have to practice on it. So here it is. Yeah, these two things, one from below, one from above, will tell us that we have balls of radius proportional to r inside the set when u is positive, and that tells us that the next step would be that this total volume, the Lebesgue volume of the boundary, cannot be 1 at point in the density cannot be 1. It has to be less than 1. And if the density is less than 1, then the Lebesgue point theorem tells you that that set cannot have positive volume. Because almost everywhere it is 1. If all points are less than 1, it means all points are the rest, which are 0 volume. Okay, so let's do the Hausdorff measure. So there is some computation involved. I'm going to go through slowly. These computations are not hard, but you have to have seen it in order to make it easy. So what we do is we want to cover the boundary. So the boundary is a very nasty set, and at each point you take a point x and you put a ball of radius r. I think I'm putting ball of radius epsilon basically here. Epsilon, lots of epsilon. Now all these things, since you're putting at every point, it means you're covering completely the free boundary. So the free boundary is completely covered. And of course, then you're taking the union of, I think I need to explain this a little bit before I go to the proof. So here's the picture. So this is the free boundary. I'm giving you a nasty picture. Okay? So I want to see what is the what is the amount of this? We know it has Lebesgue measure 0. But I would want to see that it is sort of a surface or something. I don't know that yet. So what I do is I take balls at each point, put all these balls and cover it. Okay, so it's a complete cover. I don't see, if I would color the balls with, let's say, black color, I wouldn't see the white. Okay, it's completely covering it. And then all these balls have radius epsilon or less than epsilon. And then what I do is I take epsilon to power, let's say, k, and then I have, let's say, 1 billions or 1 trillions, I don't know how many I have. So all balls. You can actually make this different radius also, epsilon I, doesn't really matter. But the key thing is that the epsilon I, that length has to go to 0. And you always have a cover and the length goes to 0. And you have, what you do then is like you take the infimum of this. Because if you have something like this, and then you cover it, or then you cover this with this one, all these radius, you see that I have a bunch of things that are extra. I don't need them. The extras are out because I'm taking infimum. Once you're taking infimum, it means that everything that is extra, you're taking out. So your picture should probably be something like this. Agree? And if anything is more here, any ball here, then you take that ball out. It's not part of your cover. You don't need that. You're already covering. So take everything which is extra, and still you don't see the white beneath this black thing. Okay? And then what you do is you take the union, the sum of all the radius to power k. And k, I want it to be n minus 1. If k is n, that is Lebesgue measure. If k is n minus 1, that's Hausdorff measure. That's like a surface. And I want to say that infimum of this, and then lim infimum of cover here, infimum of all the cover, and lim epsilon I goes to 0, is less than or equal to some constant. If that is true, that's actually going to be exactly the Hausdorff measure. If that is true, then we say that this boundary is like a surface. It has Hausdorff dimension k, and I want k to be n minus 1, and it will be a finite Hausdorff measure. So its measure will also be finite. The dimension might be finite, but be n minus 1, but not its measure. N minus 1 measure, I wanted that also to be finite. So if I can prove this, so this is what I want to prove. This means Hausdorff, or it's called n minus 1 Hausdorff, or k Hausdorff in this case. So I want k to be n minus 1. N minus 1 Hausdorff measure. This is exactly what it is. So what I'm saying, Hausdorff measure, n minus 1 Hausdorff measure will be finite. This is what I have to prove. If I prove this, then I'm done. So this part of the theory is not developed here because we are not talking about it, because that's already a different area, and you might have interest in looking at it. It is related to basically analysis, but integration when you have different dimension of spaces you want to work in. So sets can be very nasty, and you want to work with them. And fractal dimensions, when you don't really have n or n minus 1 or n minus 2, things can be in between. That's called fractal dimension. And then fractal sets, and you want to work with them. And the question is what you can get. Are you familiar with contour sets? Yeah. So contour set is a kind of fractional thing, because Lebesgue measure of that is 0, and but it is not pure point, so it's the set is large, but the volume is 0. One-dimensional volume is 0. But that set actually has a dimension, if I don't remember. If I remember correctly, log 2 or something.
Yeah,
Log 2 or something, yeah. Depending on log 2 divided by 3, log 3, something like that. Depends on if you're at the 1/3 ternary contour set or anything. So you can actually compute that. The computation is not so easy, but you can do that actually. So look at that. That gives you a different dimension than 0 and 1. And you're still in one-dimensional setting, but the dimension of that set is different. And this is about it a little bit, that I want to say that that dimension is actually, for this guy, is n minus 1. And not only that, it is finite also. You take the measure, that's going to be finite. Okay, so we cover it. Naturally, I can get so many covered. That's very natural. If it's correct. Okay, so now let me do this very slowly because there's a lot of elements here that isn't unclear for you, and even for me, I would say. So let me denote the directional derivative xi of the function with vi. This is just for simplicity, so we call it vi. I'm looking at the points when the gradient is small. So I'm looking at the points when the gradient of u is less than epsilon. Okay, so let me give you a better picture here. So I'm looking at points when gradient is less than epsilon. So again, we're just drawing a nice picture, which is easier to see. And then inside omega plus, here's omega plus, is the function here is positive. Here, I'm taking all points here. I'm saying here gradient of u is less than epsilon. I don't know how much this might go up. I don't know that. It might be something like here also. I don't know that. I don't know how the picture is. Okay, so I'm taking all points when the gradient is smaller than epsilon, but they're inside omega plus, and I'm doing a simple calculation. We know that Laplacian of u is 1 inside that domain. That's fixed. Or if it's the function f, so this is going to be larger than f to power 2, and f is larger than lambda 0. So the whole thing would be larger than lambda 0 to power 2. And lambda 0 should be strictly positive, that's what we said. That's what we need. So this is larger than some lambda 0. But in our specific case, f is constant, this is 1. Okay, so this is 1, well actually equals 1. So you go ahead, and if you compute your Laplacian, so what is the Laplacian? So Laplacian is the second derivative. So Laplacian is the second derivative, so I'm just rewriting. I'm not doing any mathematics there, basically. So Laplacian of u is this, the second derivatives of ui. And then I'm taking this to power 2. And now this is less than or equal to some constant. I don't know why a constant, but a constant probably. And then second derivatives of u to power 2. Agree? And then I'm saying this is Cn, and then di of what? Of vi. Because one derivative, I call that vi, so it's vi basically. Is it right? Oh, there should be a 2 here too, yeah? So far so good with the 2 here. And summation. And then that's it. You have the derivative is of course like the gradient. So this is like gradient of vi. I'm just rewriting, nothing special. Okay. So what is the reason for this? Well, there is of course reason for that, but I'm starting from how the proof is built, but not how the proof is taught and made. Because at the beginning you don't start with this. You start with an idea you have. But then when you want to be formal, you start with all formal things at the beginning. Which is very bad for study, actually. For study, you should start with the idea. But books cannot do that. The problem is books cannot talk to you. So a book that talks to you is good, but it's very hard to write such a book. A book that talks to you. So now let's take a compact set. So what I want to do, if I go to this picture, I want to take a compact set. The reason for that is that I'm working in a polar radius of 1. Yeah? I don't want to go to the boundary. It troubles me. I want to stay inside. So if I can do this for any piece of this domain, this is K. So any piece, I prove the absolute measure is finite, then I can just let K be different places. So the same thing I can do there. So I just cut it. And what I need is a cutoff. So I need something which is 1 most of the time, and then it goes to 0 on the boundary of K. And then I can work inside here. The only thing is that I need to take this function smooth built through maybe the function u itself so that I can cut it off. So we come to that how we build that such a function. So let's think of this. So far I don't need that. So I take K intersect with E epsilon. And remember what E epsilon was? When the gradient is smaller. You take that. And then you do the same. You get integration. The volume of this, the integration. Integration over this. And now I'm jumping 1 step here. Oh, thank you. So here I'm jumping 1 step here. Is that integration is what? The integration is over K. That's the volume. Yeah. So it's K intersect E epsilon and 1. That's the volume of it. And I'm saying that this is less than this because Laplacian of u is 1. So it's the same thing. And then you go on, and then you get this. So what I do, I take the volume and I use that Laplacian is 1 in that set, and then I use that estimate and get to a point that is reasonably good for me to work. So far so good. Yeah, I'm actually enlarging it. If I go from E epsilon to this domain, I'm enlarging it. Agree? You can see that as a little bit of homework. So try to prove this. You see, E epsilon is defined differently. It is that the gradient, remember, gradient is less than. And now I'm changing it a little bit to Vi is less than. So gradient of u is like V1, V2, V3. Now I'm just taking separately each Vi and then adding up over I. I'm making it actually larger. So I'm making this domain a little bit larger. Agree? That this is a larger, so it's okay. So what happens with Vi? So Vi is the derivative of u in direction xi, and then I'm taking the plus part of that. So that function might be negative at some places and positive at some other places. I'm taking the positive part, I'm taking the negative part. And this is an important point, and this is an exercise for you to do at home. So here's the exercise. So VI is positive here. Let's say VI is negative here and VI maybe is 0 here. I'm giving you a very good picture. It's not necessarily so. And then I'm looking at, and I know that Laplacian of VI is 0. Is Laplacian of, okay? That's just rewriting. When VI is positive, when VI is not 0. Or interior of the set, in the support, interior of the support of VI. Now I'm saying from here it follows that Laplacian of VI plus part is actually a subsolution, and Laplacian of VI minus part is also a subsolution. VI plus is supremum of VI and 0, and VI minus is supremum of minus VI and 0. Okay, this is an exercise for you to prove that if you have a function, actually you might even have the proof in the Evans book or something, yeah? If a function is 0 and non-negative, okay, 0, so VI plus is 0 here, 0, and then it's non-negative. And Laplacian of this function is f or g or whatever you want to in this set. This function's Laplacian will be Laplacian of g on this set, and 0 outside, and something appears on the boundary. This is our discussion about the problem we had at the beginning. That measure will be positive. So there will be a measure which is here, living here on the boundary of this support, but that's positive. So I can say it's larger than or equal to 0. It's a good exercise. So I think we can keep this as one of the exercises. It's question mark. Okay, it's larger than or equal to 0. I can rewrite this. The weak formulation of this is what? Is exactly this. If a function is subharmonic, it means you can take the product with eta, take the product with eta, integrate, that's non-negative. Eta is non-negative function. Take the product with eta, this is eta. Not gradient, but eta itself. Take the product for non-negative one and integrate, this will be non-negative. Integration by parts gives you this. Okay, you may try to verify this again. Now you should be able to verify it quite fast after all the lectures. So take integration, multiply it with eta, integrate it. If this is non-negative, the product is non-negative because I'm talking about non-negative etas. Yeah, non-negative etas. And then integrate, and then use integration by parts. Go to the gradients. So we'll have this inequality. Keep in mind that we have non-negative eta, compact support, and all that. Okay, so let's go on. Are you okay with this? So what I'm done, I'm actually taking the volume of this cover, here, and I'm estimating it with the gradient of VI. VI is the derivative of u, so I'm grading it, I'm estimating it with the gradient of second derivatives, with the second derivatives of u, and not second derivative of the function u. And I want even actually go further. I will end up with the third derivative very soon. Okay, now we need a device. You remember such a device we had at the beginning also. So take eta now to be a smooth function, compact support, and it's going to be 1 here. on this k, and I will let it to be 0 very fast. But it has compact support, and I'm taking, so that's phi, but I'm taking another function. If you go back to the first lecture, second maybe, we had such a function. That you you do the cutoff with the help of the level sets. That's a very strong tool, because you're using the function itself strongly. You don't care about the regularities, anything. You just use the function. So that's a value t, and whenever t is negative, whenever this guy is negative, you put 0. Whenever it's between 0 and epsilon, you put it like this. And once you reach epsilon, then you put it 1, because at epsilon this will be 1, so you just continue with 1. And now you realize when you put v here, vi, it means here you have the derivative of u. In the other problem, we had the function u. Now we have the derivative of u. That's very helpful for us. Okay, so what is written here is gradient of v. So this is what I'm rewriting. So think of this, gradient of v times gradient of eta. Now I'm changing eta to this guy, and I have to write the gradient of this one. So gradient of this whole thing. So I'm not doing anything but coming with a clever idea of a function, which might be very helpful for me, and I'm just putting this here. And I know the whole thing here is less than or equal to 0, according to previous page. So this is less than or equal to 0. That's what's written there. So what I want to do is rewrite this. Rewriting means just going with the gradient and compute it. So this is already here. One of them is here. This is already here. So what I'm doing is I'm using product rule and the chain rule. So product rule gives me 2 pieces. One piece, second piece, and then when you're applying gradient on this function, chain rules tells you that one of these guys' gradient has to come out, and that's one of them. That's the reason you have 2 here. So one is here and one comes out. That's the reason you have 2. When it comes out, you get this epsilon minus 1 with it. That's the reason you have epsilon minus 1. Okay, and the next one is no tricks, just write it. So this is complete rewriting and nothing surprised there. This, if you only know calculus 1, not even 2 variable calculus, you should be able to do this if the gradient is just 1 derivative. Okay, so, and this is the set when vi is between 0 and epsilon. I'm doing for both of them, both plus and minus. So you can think of this as one equation for plus and one inequality for plus, one inequality for minus. So let's see what happens. I just define the second derivative like this, the sup norm, and I go, so let me go back. I go to, is this what I'm using? Yes. So what is this guy here? So this is not negative, so I forget about this, so I have this one. Agree? I have this one. It means that I have this one and I have to estimate it with this. I take it on the other side and estimate it. So here it is. So this guy here I have, epsilon minus 1 is still here. And that phi here, I took it out because it's 1. I said on k is 1. So if I go over k, that integral over k with 1 will be less than the previous integral with the phi here. So this will be less than the phi here. And that was already smaller than, that was already smaller than with the gradient. So I go in with the gradient. I just carefully have to put everything in this place. So there's no surprises here. Nothing that really is of any surprise. The problem is this guy here. Let's see how we can get rid of that. And then this is gradient of vi, that's the second derivative of u. Second derivative of u, I call it n. And now you realize that you need that the function is C11. So here I use that. And I use what? I use the non-degeneracy at that spot here. the Laplacian of u is larger than f, and f is strictly larger than 0. So I called it 1 all the time. But okay, now you sum up overall I between 1 and n, and you get that this volume here, you see, no, I erased that, I'm sorry. So, okay, so we saw that this volume could be estimated through this. I think there are a little bit of details here that you, you don't see.
How did you get that epsilon? From the left-hand side, epsilon has gone on the right hand.
Yes, yeah, you can just put this on the other side, so the whole thing is less than this. Yeah, I didn't have epsilon there in my computation. So if I put epsilon here, take a product with epsilon, you will have this gradient is less than epsilon times that m. That's exactly what it is. And I had the estimate for k intersected with epsilon. Yeah. So there are no further details. Okay. But if you realize what is the volume, Lebesgue measure is this epsilon here with n, not n minus 1. So Lebesgue measure is with n. And then I have the estimates that if I take the Lebesgue measure of this guy, the Lebesgue measure of this guy actually sort of approximate Lebesgue measure will be going to 0 fast enough with epsilon. So if I take this epsilon on this side, this is what I'm getting. So approximate Lebesgue measure goes to 0 fast, so the Lebesgue measure will be 0, but it goes fast with epsilon. So it means that I can take that epsilon on the other side, and that gives me Hausdorff measure of n minus 1. If that epsilon on this side would be, let's say, square root of epsilon, then it would be a different measure. Okay. Now, in order to really do from that part, that estimate, you're at the level of epsilon, you have to go to the limit. In order to go to the limit, you have to do this covering. So these are some details, background details you have to do. So you do a covering, then you take like the Sikovich's, you have the finite covering, so you can have a covering. That these are standard techniques in analysis, that if even you have billions of covers, you can take them out and have finite number of coverings. But think that it's in dimension, let's say 2 even. Are you forced that you cover some set with a bunch of things, and some part of the sets can be covered, have to be covered with sequence of infinite numbers? And the answer is no, you don't need to. It's dimensional dependent. I think it's 5 or something, 5n or something like that, I don't remember. So the Sikovic covering tells you that there is a finite cover depending on the dimension. That in dimension, because you don't see it now, I'm giving you pictures in dimension 2, but in dimension 1 billion, you don't see it. So you cover a set, and then let's say your set is, you want to cover something that's very tiny, and you want to cover it with tinier balls. But the question is, when the balls become tinier, you might need to overlap a little bit more. So several balls are coming in. Some pieces of them are the same, and you're computing them. In this, you're computing. You don't like that. But what you say is that there is the Sikovic says is that there is a finite number. It's enough to have the finite numbers for each point could be infinite numbers. That's very important. And once you have that, then it means that you can actually do this. All you need to do is put a constant n here. That n here, it comes in, finite covering. And then you get this, basically.
So that n does not depend on the cover.
It depends on the dimension. Yeah. It depends. This is measure theory. It is a little bit advanced measure theory, the Sikovic covering. You don't really see that in master classes. PhD student analysis will see that. So you go, that's what I'm doing. I'm taking the volume of the ball, that's like epsilon to power n. So the volume of the ball is like epsilon I to power n. and then some constant, which I don't care. And this is less than, now this is less than this. Why is that? That's also a jump we do. So do you agree that this volume is smaller than this volume up to a constant? That's non-degeneracy. Do you remember yesterday we said that if you take the support of the set, then you have always balls inside of proportional radius? This is exactly what it is. I'm saying that this volume is always less than this volume up to a constant. So it says that this intersection, it says the following. If you take any ball like this volume is proportional to the whole volume of the ball. Because you can always have a ball of the same, not the same, but a constant, fixed constant times radius somewhere. This is a very important fact, and the proof of that was the non-degeneracy proof. And then you estimate it with the CEMS. So now I have to go, either I have to go to change my proof a little bit, or I will say, okay, since I've done everything now, instead of taking epsilon, E epsilon, I take EM epsilon. All gain is the same, basically. And then I get this estimated all the way. And then you're done, basically. These are small technicalities that one has to do. But at the end is that you get actually this estimate that I was telling you about. That you get this estimate. Oh, don't worry about K prime here. That's a technical matter. There's small technicalities. This is like the fine structure of the whole proof. And then you get the volume is bounded like this. And this is exactly the infimum, lim infimum. And you're done. That's it. So dimension will be less than constant, and the measure will be less than constant. So Hausdorff measure of the whole set of the free boundary is controlled. So I would challenge you to read the proofs here in detail. And then you already have the file. Read the proofs here. Every piece needs some real caring. I didn't go through every details here because you have to really work with the Hausdorff dimension and measure familiarity with that.
So this only says that the n-1 Hausdorff dimension, Hausdorff measure is finite. It doesn't say it is exactly equal to.
No, it says that Hausdorff n-1 dimensional Hausdorff measure is finite. Not the dimension is finite. Also measure is finite. If you get the measure is finite, then the dimension is finite.
Yeah. And it is not exactly equal to n-1.
It is exactly equal to n-1. Hausdorff dimension is n-1. Is n-1, but even more, I'm saying that even its n-1 dimensional measure is finite. It's universally finite like this. Because the function sine of 1 over x, that has a one-dimensional Hausdorff measure, but the measure is infinite. So I'm saying that I can control it with all the ingredients. It's universally controlled. So the universality is here. So after the break, I'm gonna not go into this. I will start with this tomorrow. I will try to do the proof I told you about, the one-line proof, and talk a little bit about monotonicity formula. That's a little bit sidetracked, but I sidetracked in the sense that it's related completely to this. But there's very beautiful ideas. I will do it at the heuristic level. And then tomorrow we will start, so we are 1 day ahead, I guess. You have to slow down.
You need to.
I'm going too fast, yeah?
No, it is fine, I think. It's at least, I think we are following. They may have to go and work a lot probably, but I think it's not ununderstandable or too fast, I think.
If I would put the percentage of this from 0 to 100, how much would you say that we follow? coming closer. Who would say I understand 10% of this? At least 10%.
I think they understand more. I think so.
Yeah,
They are
I'm saying
not
at least. I'm saying at least.
Yeah. Yeah, I think they will feel comfort because means when I'm doing the tutorial, they are kind of
Not today. Today this is tough.
yeah.
So no, I'm not talking about today. Let's say yesterday or the day before. If I take the 2 days accumulated, who understands more than 10%? Okay, there's one. Of course. 20%? Let me start with each one of you. What do you think? You say 10 at least? 20?
At least, yeah.
At least.
Above 20.
Well,
At least 20.
It's 25.
okay, that's good.
10 to 20%.
I would say 30.
That's very low. I thought you should say 50%. Like somebody would say 50%.
Well, that's what I'm saying. No, I mean,
Because
I because I'm here, I can see them. You don't see them. I mean, this is like.
Yeah, because this is I think for the first time,
Yeah.
and they do not have like they have zero PDE
Yes.
background. Okay, it means at least those students there they have zero. Means the remaining three are still doing PhD, and means the two of them at least have taken some reading or some course with me, but those are zero PDE. So if they are understanding more than 20%, I should be very happy because at least I know that they will study further and they will try to, if they develop affinity for it, maybe.
So we're having break at 3 o'clock, yes? So.
Yeah.
I was going to suggest earlier break, or maybe if you want to do something tutorial, you can do. Because I think.
Yeah, I was doing that approximation thing. Do you want me to do it?
Yeah, then you can do that, and then I can do.
The T guy may not. I will try because the T guy may not come early, but.
No, this is what I'm saying. Then I can do after break. At 3 we take break, and then I can do the monopolistic formula. Because the monopolistic formula is also something I want to discuss.
Yeah, I mean, I
I will need 1 hour for that.
Yeah, and I want to understand that.
So it means that if I start now, I have to break. So let's do that after the break. So if you want to continue or if you want a longer break, maybe you can let them do some exercises.
Yeah.
So let's see. Pick up one of the exercises.
No, I think they solved in afternoon. That is what they have done. Do you want me to do that?
You can just stay over there because I will go and
There was that one. You can do it. Yeah, I will tell you. Or at least that will give us another chance to go back to it. She has to report to college.
What does it mean?
You want to spend half an hour discussing that? We can do that.
Like our college is undergoing some accreditation, which is national level.
Yes.
So I will have to leave by 3.
Oh, you have to leave earlier. Sure, of course.
So she's saying you can tell the one line now, and she will hear and go. Or then she said that I can tell her later on. So I said it's better I tell her later on maybe. Because that's something interesting.
You can write one line for you.
No, but it's not going to make much sense, I think.
No, I was going to develop around.
No, you develop it, please. We want that. So
yes, you can explain. Maybe, I mean, you have the video.
Yeah. So if you want, you can early and make your